In the autumn of 2023, an astronomer at Yale named Peter Van Dokkum was paging through an old Hubble image of a distant galaxy merger when he noticed something that shouldn't have been there. A thin, straight line of light running away from a galaxy's core for 62 kiloparsec, roughly 200,000 light-years. Long enough to stretch across the Milky Way twice over. It looked, at first glance, like a scratch on the detector. It was not a scratch. Over the following 2 years, it became the strongest evidence anyone has ever gathered that a supermassive black hole can be thrown out of its own galaxy and sent racing through open space, dragging a wake of newborn stars behind it, like sparks off a grinding wheel. NASA's language, once the confirmation landed in December 2025, was celebratory. Headlines called it a first, a triumph, proof of a 50-year-old prediction finally caught in the act. Read the paper itself, and the tone is different, careful, hedged in places you wouldn't expect. And buried in the acknowledgments is something the headlines never mentioned. The team had gotten a piece of their own earlier story wrong, and the December paper quietly walks it back. Here's what is actually sitting in the data. A trail of gas and young blue stars, 200,000 light-years long, anchored to nothing. A sharp, sudden jump in gas velocity right at its tip, the unmistakable signature of a shock wave. A black hole, unseen but massive, that the physics says has to be there to make that shock wave happen at all. And underneath all of it, a name almost every outlet used that, if you go back to the technical papers, turns out not to be quite right. Any one of those threads is a curiosity. Together, they are a black hole loose in the universe. Wherever you're watching this from tonight, I want you to sit with something uncomfortable for a second. Every picture you've ever seen of a black hole, the swirling orange disk, the dark circle at the center of a galaxy, has one thing in common. The black hole stays put. It's the anchor, not the object in motion. What if that isn't always true? What if every so often the anchor comes loose? Here's the argument I want to walk you through tonight. Webb didn't just photograph a runaway black hole. It caught the physical proof, the exact kind of proof theorists have been waiting 50 years for, that a supermassive black hole was kicked out of its home galaxy by the collision of two smaller black holes, and that it is now moving through intergalactic gas fast enough to outrun the galaxy that made it forever. And along the way, I want to show you where the press coverage quietly simplified a much messier, much more interesting story, and where the scientists themselves had to correct their own earlier claim. The object now has a name, RBH-1, short for Runaway Black Hole 1. Van Dokkum first flagged the linear feature in a 2023 paper in the Astrophysical Journal Letters, working from archival Hubble imaging of a galaxy at redshift 0.96, meaning its light left home roughly 7.5 billion years ago, when the universe was about half its current age. He proposed, cautiously, that the streak was the wake of a black hole ejected from that galaxy, compressing gas as it went and triggering a trail of star formation behind it. Cautiously is the operative word. A 2023 Hubble image, however striking, cannot distinguish a runaway black hole's wake from a few other, far less exotic explanations. A team led by Mireia Montes and Jorge Sanchez Almeida published a rival reading the following year. Deep Hubble imaging, they argued, was more consistent with an ordinary bulgeless galaxy seen edge-on than with an exotic ejected black hole. That paper is real, it is published, and for roughly 2 years, it was a legitimate open question. This is the part most of the December headlines skipped entirely. The runaway interpretation wasn't confirmed the moment it was proposed. It survived a genuine, published challenge. What finally separated the two explanations wasn't a prettier picture. It was spectroscopy. In December 2025, Van Dokkum returned with a team of 8 collaborators and pointed Webb's NIR spec instrument. in its integral field unit mode, directly at the tip of the trail. NIR-SPEC doesn't just take a picture. It builds a velocity map, pixel by pixel, of the gas glowing at that location, using the oxygen and hydrogen emission lines redshifted by the galaxy's expansion. What they found at the very tip of the trail was a velocity gradient of roughly 600 kilometers per second, packed into a region about 1 kiloparsec across. Translate that. A bulgeless galaxy, ordinary and edge-on, doesn't do that. Gas doesn't jump its speed by 600 kilometers a second in the space of 3,000 light-years, unless something massive is physically plowing through it, faster than the local speed of sound in that gas, hard enough to pile it into a shock front, the way a boat's hull piles water into a bow wave. That is the specific, narrow signature of a supersonic bow shock. And a bow shock needs a mass moving at the front of it. Here's the part that should actually stop you. From the velocity of the shocked gas, the team could back out the velocity of whatever is driving it. The number they got was close to 1,000 kilometers per second, about 2.2 million miles an hour, roughly 1/3% of the speed of light. That is fast enough, given the mass of the galaxy it came from, to permanently escape that galaxy's gravity. Not slow down and fall back in a few 100 million years. Gone. For good. For an object with the mass of at least 10 million suns, reaching that speed is not a small ask. Van Dockum told Space.com, describing the discovery, that it boggles the mind. He wasn't being loose with language. The amount of energy required to accelerate 10 million solar masses to 1,000 kilometers a second is difficult to produce through any gentle process, which narrows the list of things capable of doing it down to almost nothing. Sit with the number for a second longer. 1,000 kilometers a second is roughly the distance from New York to Los Angeles, covered every 4 seconds. It is faster than nearly every other massive object cataloged in the observable universe. Stars don't move like this. Galaxies don't move like this. In the entire history of astronomy, no confirmed supermassive black hole has ever been clocked at a speed like this one. Because until December 2025, no one had ever caught one in the act of actually leaving. There are, in principle, 2 ways to kick a supermassive black hole out of a galaxy. The first is a 3-body interaction. 2 black holes are already orbiting each other when a third one wanders in. And gravity, working out the encounter through pure Newtonian slingshot, flings the lightest of the 3 out at high speed. The second is stranger. When 2 black holes of comparable mass finally spiral together and merge, the gravitational waves they emit in the last instance aren't perfectly symmetric, especially if the 2 black holes are spinning at different rates and angles. That asymmetry carries away momentum in one preferred direction, and by Newton's third law, the newly merged black hole recoils in the opposite direction. Physicists call it gravitational-wave recoil, or a relativistic kick, and for 50 years it existed only in equations and supercomputer simulations. A 3-body ejection is not a longer version of ordinary black hole wandering. A gravitational wave kick is not that either. Both are rare, both require special circumstances, and distinguishing between them from a single object's velocity alone is close to impossible. What isn't close to impossible is working backward from the speed itself, and that is exactly what a second team did 7 months after the JWST confirmation. In July 2026, Tausif Islam, Tejaswi Venumadov, and Digvijay Wadekar, working out of the Kavli Institute for Theoretical Physics at UC Santa Barbara, published a follow-up in Physical Review Letters. They took RBH1's measured kick, 954 kilometers per second, with an uncertainty of roughly plus 110 and minus 126, and ran it against a library of numerical relativity simulations of black hole mergers, checking millions of combinations of mass ratio and spin to see which ones could actually produce a kick that large. The answer that survived the filtering was specific. A progenitor binary with a mass ratio no more extreme than about 6 to 1. A larger black hole spinning rapidly, with a dimensionless spin around 0.75, and a binary that was precessing, wobbling on its axis, in the final approach before merging. That merger, they calculate, happened roughly 70 million years before the light we're now receiving left the galaxy. And the properties of the progenitor black holes imply their host galaxy, cataloged simply as GX, was likely built from a major gas-rich collision between two galaxies of comparable size. Here's why that detail matters beyond satisfying curiosity. The kind of merger the Islam team reconstructed, a spinning, precessing, roughly comparable mass black hole binary, finally overcoming what astronomers call the final parsec problem, and coalescing, is close to the ideal target for the European Space Agency's Laser Interferometer Space Antenna. LISA is a 3-spacecraft observatory, arms 2.5 million kilometers long, under construction now for a planned 2035 launch on an Ariane 6 rocket, budgeted at roughly €1.5 billion. The Islam paper estimates that mergers like the one that produced RBH1 could show up in LISA's data with a signal-to-noise ratio above 1,000. Not a marginal detection, a textbook one. RBH1 isn't just a striking picture. It's a preview of what a billion-euro instrument, still 8 years from launch, is being built to listen for. Now, for the part that bothered me most while researching this, go back and read the wave of coverage from mid-December 2025. Space.com, Science Alert, SlashGear, half a dozen others, all describing RBH1 as sitting inside a system called the Cosmic Owl. It's a vivid name, and it's stuck. There's just one problem. Go back to the actual astrophysics literature, and the Cosmic Owl, also called the Infinity Galaxy, is a different object. It's a separate ring galaxy merger, discovered independently by a team led by Mingyu Li, containing not one runaway black hole but 3 active supermassive black holes still embedded in their host galaxies, at a different redshift, roughly 8.8 billion light-years away rather than 7.5 billion. The peer-reviewed paper confirming RBH1 refers to the Infinity Galaxy only in passing as a contrasting example of a different phenomenon entirely, and gives RBH1's actual host galaxy a separate unglamorous label, GX. I don't think this happened out of dishonesty. 2 genuinely strange, genuinely real discoveries came out of the same research group within months of each other, both involving supermassive black holes behaving in ways textbooks said they shouldn't. And somewhere in the retelling, a punchier existing nickname got attached to the wrong system. That's not corruption. It's the ordinary friction of translating a technical paper, with its careful qualifiers and its separate object catalogs, into a headline that has to fit in one line and get clicked. But watch what the softening does anyway. Candidate becomes confirmed a little earlier than the data strictly allows. A distinct, contrasting object becomes the setting for the story, because the name is better. None of it is a lie. All of it moves the reader's confidence further than the paper itself would justify. One small substitution at a time. This is also not the first time a settled picture of black holes and their galaxies turned out to be far more provisional than it looked. 20 years ago, the working assumption was that every galaxy above a certain mass keeps its central black hole for life, that the two grow together in lockstep, co-evolving, practically inseparable. Then came a slow drumbeat of exceptions. Galaxies discovered with black holes far lighter than their mass would predict. Galaxies where no central black hole could be found at all. Ejected black hole candidates flagged in survey after survey, most too ambiguous to confirm, a handful, including this one, eventually nailed down. Every one of those cases looked, on first discovery, like an anomaly to be explained away. none of them were. RBH1 is not an exception hiding at the edge of the data. It's what the data looks like once you're finally able to see it clearly. Let me pull the actual findings together, because there are several and they're easy to lose track of. A linear trail flagged in 2023, initially ambiguous with a competing bulgeless galaxy explanation that was taken seriously by other astronomers for 2 years. A December 2025 JWST spectroscopic follow-up that measured a 600 km per second velocity jump across 1 kiloparsec at the tip of that trail, the specific fingerprint of a supersonic bow shock, which the ordinary galaxy explanation cannot produce. A black hole velocity, backed out from that shock, of roughly 1,000 kilometers per second, fast enough to escape its home galaxy permanently. And, 7 months later, an independent reconstruction, narrowing the cause down to a specific, precessing, unequal mass black hole merger, roughly 70 million years before the light we're seeing left home. Let me be specific about what I am not saying. I am not saying NASA or ESA misled anyone, and I am not saying the astronomers involved did anything but excellent, careful work under real observational limits. Van Dokkum and his collaborators corrected their own earlier claim about a possible second wake on the far side of the galaxy once deeper imaging showed it wasn't there, which is exactly what good science is supposed to look like.